This is the second presentation on projectile motion, where we focus on calculations and air resistance. These are the performance standards that will be covered in the following presentation. What you should have now is your own copy of the performance standards in front of you, and as we go through them with the slideshow, tick off the ones that we cover when you have understood them. The equations listed on this slide will be used when performing projectile motion calculations. I'd like you to pause the video now and write these down in your notebook because we'll be referencing them a lot. I'd also like you to have a look at your formula sheet that you've been given and find these equations on there. So there's some variables that are used when talking about projectile motion, which are listed on the right, and they include the initial velocity denoted by V0, the final velocity denoted by VF, distance denoted by S, which is not to be confused with seconds, the units of seconds, time, which is T, and acceleration with a lowercase a. You need to be able to perform calculations for both horizontal and unilevel projectile motion. Horizontal projectile motion is when the projectile is launched directly horizontally and then falls to the ground, where unilevel projectile motion is when the projectile is launched at an angle upwards and then falls to the ground after. So you need to be able to calculate the time of flight, the range, the velocity at any time, and the maximum height to which it rises. So to calculate the time of flight for a parabolic path, meaning unilevel, we can use this equation. Now this equation has the symbol U, which is also denoted in previous slides as V0. So it represents the initial velocity. For horizontal projection, the time of flight can be found using the second formula. So let's look at an example question. So given the initial velocity of a projectile, calculate the vertical component of velocity at any instant. Okay, so our example is a ball is thrown downward at 2 meters a second. How fast would it be traveling 1.5 seconds later? So we can use this equation, which you can reference your notes that you took before, and it's on there. So we're looking for the velocity, which is v. We're given the initial velocity as 2 meters a second, but notice in the calculation here that we've written a -2. That is very important, as we have assumed that up is positive, which is a common assumption to make in projectile motion questions. Following further in the equation, we use acceleration and time. So notice acceleration is also negative, and is the acceleration due to gravity, and it's negative because it also acts downwards on the object. And time is 1.5 seconds, and time is always positive. So if you actually do end up using or finding an answer where time is negative, recheck your calculations. But it's a matter of just solving this equation, and we get our answer of 16.7 meters a second. The negative suggests that the object is traveling in a downward direction. This slide covers some commonly asked questions in the equations that we use to find them. So to find the range of a projectile, we're looking for S, which is the variable that we use for range. And what we want is the horizontal component of the velocity. We also are looking for the time. So we want the horizontal component, as the horizontal motion is constant, and with the distance that it's in, with the time that it's in the air, will give us the distance. To find the velocity of the projectile at any time, either in the y direction or the x direction, we use the following equations. To find the resultant velocity, we actually perform a Pythagoras calculation using a right angle triangle. And you can see the equation written here is a variation of that with the velocity instead of the commonly seen A, B, and C. To find the maximum height of a projectile, we use the following equation, where you can see the y component is the most important component when we're looking at the maximum height. Now we're going to have a look at an example calculation. So let's consider a projectile launched at 10 meters a second. And this is 45 degrees above the horizontal here. Okay, so have a look on your equation sheet for this equation here and this equation here. Instead of the u's, they might be v's, but represents the same thing. So what we've done here is we've worked out the x component and the y component of our initial velocity. And we can find that when it's 45 degrees, the x and y component have the same velocity. So let's find out how long the object was airborne for. And this time we focus on the y component using this equation. Now, when we use our projectile motion equations, we always focus on either the horizontal or the vertical components of velocity. And this way it makes our calculations a lot easier. So when you find the equation, determine whether you're going to use it horizontally or whether you're going to use it vertically. So looking at this equation, we've got Vf, which is here. Now looking vertically, our Vf we can select to be 0 at the top of the projectile's motion, because in the vertical direction, the projectile is not moving in the vertical direction when it's at the top. So this is what I was saying when the calculations become easier. So our initial velocity we calculated before, our acceleration is due to gravity, and we can see we've written a negative there, and time is actually what we want to determine. So substituting the values, rearranging the equation, we find that our time is 0.72 seconds in this case. But remember, we were looking at the final velocity at the top of the projectile motion, but this is only the halfway point. So what we have to do is to multiply it by 2 to work out the time that it takes to come down as well. So the total time that the projectile was in the air for is 1.44 seconds. Now we can finally calculate the range, and we can use this equation here, and we end up with our value of 10.18. If we did some calculations for a given velocity, however a changing angle, we might end up with a graph like this. So what we can see here is that our maximum range based on a certain angle is when the angle is 45 degrees. So you can see that with the blue line, and the maximum range is just over 90. If we launch the projectile at any other angle, our range will not be as far. Now what we also notice, if we can compare a couple of values, so if we look at the 80 degrees here and the 10 degrees. So if we launch the projectile at 80 degrees, we get a range that's just over 30. And if we launch it at 10 degrees, it's also just over 30. Okay, the same happens when we use 70 and 20, 60 and 30, and 40 and 50. Okay, so what we can see a pattern here where the angles are complementary, adding up to 90, then the range will be the same for a given velocity. Introducing air resistance now. Air resistance is a force which acts in the opposite direction to the motion of the projectile. So looking at this diagram that we've got here, we can see the motion of the projectile is given by the blue arrows. So we've got one arrow there, another one here. And you can see they're pointing along the path of the projectile. Now, the air resistance acts directly opposite that. So in the opposite direction of the velocity. So air resistance depends on how easily an object moves through the air, and it increases with speed. As you can see below, there's written the formula for air resistance. Now, you will not be required to perform any calculations using this formula, however you may be required to discuss it in a short answer. Also, this formula is not limited necessarily to air, but resistance in any fluid. So velocity is one of the variables, and it affects the air resistance. So the faster the object, the greater the resistance. And what we can notice is that the velocity is squared, and this means it's the most important factor in determining the magnitude of air resistance. Another factor is the density. So cold air is denser than warm air and produces greater air resistance. The area of the projectile is also important. So a bigger object will have greater air resistance, such as a parachute, for example. The factor of CD is the drag coefficient, and this relates a lot to the shape and surface area of the object. So a rough, irregular object will have greater air resistance than a smooth, regular object. We don't need to go into detail about this, but you'll just have to mention it if it was raised in a question. So what effect does air resistance actually have on the projectile motion path? So looking at the vertical component, as the object rises, the vertical component of air resistance is in the same direction as the gravitational force, so it's acting down. The vertical component of the velocity will decrease more than if it was in ideal conditions, such as in a vacuum. The time taken to reach the maximum height will therefore be reduced. As the object starts to drop towards the ground though, the air resistance will actually be acting in the opposite direction to the gravitational force. So the vertical component of the velocity will increase less rapidly than in the absence of air resistance. This will tend to increase the time taken for the object to return to the ground from its highest point. So the time taken for the object to return will be reduced because of the decrease in the maximum height. So overall, based on the object traveling up and then traveling down, the flight time will be decreased overall, but not greatly. So now looking at the horizontal component when air resistance is present. So the horizontal component of air resistance is opposite to the direction of motion. So the component of velocity will decrease rather than remain constant throughout the time of flight. This, together with a reduced flight time, will reduce the range of the projectile. The projectile will fall more steeply than it rose, so you won't get the symmetrical parabolic shape that you would in the absence of air resistance. As part of the SACE curriculum, there's some application components of each topic where you apply your knowledge into a physical field. So for the projectiles section, you apply it to sport. So this slide will cover this section. We have to look at the extent to which air resistance affects various projectiles in sports. So it's kind of summarizing what we went through in the last couple of slides. So what sports will be affected by air resistance? So the extent to which air resistance affects various projectiles in sport will be determined by the speed, shape, size, and surface texture of the projectile. It will also be affected by air density. The mass of an object, though, does not affect the amount of air resistance, as it is not present in the equation, but it does determine the degree to which a projectile is affected by the air resistance. So what this means is that a light projectile will be affected more than a heavy, and that's because of the force. So the force will have more influence on a light projectile than a heavy projectile.